And welcome back to Ms. Sogram's Maths, and today we are looking at a probability concepts paper from the D&D Resources, and it's practice external assessment number 4. This is from their booklet that is made for the external 91585. So a thank you to D&D Resources for allowing me to use their materials in this way to make these worked solution videos for you. I have put a link in the video description to their website where you can order these booklets. I highly recommend that if you don't already have a paper copy of these, then you go and buy one. They are excellent preparation for these externals. Right, let's take a look at question 1. Now these types of questions I always find easiest if we can make some kind of picture or diagram from it. I'm going to do a Venn diagram. You could possibly set this up as a table as well. So we've got two possible sort of categories here, that they have to have a blood test or be referred to a specialist. Okay, now let's put the information in, and we're doing this Venn diagram as probabilities rather than absolute numbers. So the probability that they visit the doctor and they don't have to have either a blood test or be referred to the specialist is 0.38. So we have that on the outside of our circles, so everything else. Of the doctor's patients, 0.32 are referred to a specialist, so the probability total for S is 0.32. Then the probability that they are referred for a blood test is 0.44. So that means that the whole of the circle S adds up to 0.32, the whole of the circle B adds up to 0.44. Now if we do 1 minus 0.38, oops, there we go, 0.38 is equal to 0.62. So the total that's inside both of those circles can only add up to 0.62. Now if we add these together, we get 0.76, which means that we've got an overlap there. There will be something that's there in the middle, and however much extra we've got will be the amount of overlap. So if we subtract that, it's 0.14. So we have 0.14 in the middle here. Now let's check if we need to work out the other pieces. So B adds up to 0.14, so 0.44 minus 0.14 would give me a 0.3. Just here where they need a blood test but not referral to the specialist. And the ones that only need a referral to the specialist without the blood test will do a similar thing here. So take off the 0.14 and that's 0.18. So now those three inside of the circles will add to 0.62. And we got the 0.38 on the outside, making 1 altogether. Okay, now back to the question, what are we being asked to work out? That a random patient requires both a blood test and a referral to the specialist. So the probability of B and S is equal to 0.14, that piece in the middle. Okay, for part B, we've got that the doctor is seeing patients categorized as male or female, and a single patient is randomly selected in the morning. So the morning patient could be female or male, and then the afternoon patient also gets randomly selected, and they also would be categorized as female or male, female or male. Now let's put some information together. The doctor sees 12 patients in the morning, 3 of which are male. So 3 out of 12 were male. So then the probability of picking a female, if we take that 3 off, we've got 9 out of 12. Then in the afternoon, he sees 12 male patients and an unknown number of female patients. So in the afternoon, he would have 12 out of n. We don't know the number of patients yet. And then this would be 1 minus 12 over n. Same for the bottom branch here, 12 over n, 1 minus 12 over n. Next, we're told the probability that both patients are the same sex is 0.05. So the branches where that happens is if we get female-female or male-male. And we know that they will add up to a total probability of 0.45. So the FF branch is 9/12 times by 1 minus 12 over n. and the male is 3/12 times by 12 over n, and that's equal to 0.45. Now, to save ourselves a bit of time and energy, let's just pop that into equation solver to work out the n. So let's type that in. 9/12 times by 1 minus 12 over, I'm just going to call it x in this, just for easy entry into the calculator, and then add on 3/12 times by, oh, I needed a bracket there just to make sure. Actually, it probably was fine without the bracket, but I just want to make sure I'm keeping track of what I'm doing here. Okay, and then that is equal to 0.45. So enter that, solve, and we have 20 is the solution to this. So n is 20. Now, remembering what n was, that was the total number of people that were being seen in that afternoon. And what we're being asked for in the question, we want the number of patients the doctor sees in the afternoon. Okay, moving on to the next bit. So we have this scratchy card. Some important information that we know about it is that the win to lose ratio is 2-to-1. So there's twice as many winning ones as losing ones. So if we have 12, that means that there are going to be, if we divide that 12 by 3, then that's a 4, and 2 lots of those would be 8 winning and 4 losing. Now, to get a win, we need to have 3 or more win circles revealed. We can only scratch up to 4. We want to calculate the probability that a random customer wins by only having to scratch 3. So basically, they get it in their first 3 scratches. So what's the chance of that? Them finding 3 wins in a row. So probability of win, win, win. Well, to get a W on the first one, we have 8/12. Then we would have 7 left out of a possible 11 to pick from. Then we would have 6 winning ones left out of the 10 that are left. So 8/12, 7/11, and 6/10. Which, as a decimal, is 0.2545. For part 2, we need a diagram to show what could happen here. Now, we can only do 4 scratches, so the easiest thing to do here is probably a tree diagram. So scratch number 1 could be a win or a lose. Scratch number 2, again, could be a win or a lose. Okay, now, if we get 3 wins or 2 loses, then the game is finished, because that means that you have won or lost. So just reminding you of those rules up there. We had 3 or more wins, but lose if 2 or more loses are revealed. So once we've got these 2 losses from this branch here, the loss, then we don't need to carry that branch on. This one here, if that goes to a win, again, we've won, so you wouldn't have to scratch another one. So win, win, win would stop there as well. But we could have win, win, lose. We can do this next bit here, win, lose, can go to win, lose, and then win, lose. Now this branch here would stop because we've got 2 L's along that one. Okay, so in fact, I'm going to spread that just out the way a little bit because we don't need any more room for the one underneath it. Okay, so this branch is done, but this one isn't. This one we could get a win, we could get a lose. On this one here, we don't have 3 wins and we don't have 2 losses, so we can go win or lose. This branch has got 2 losses, so we wouldn't carry on with that one. This one would be win or lose, and this branch stops there because it's got 2 losses. Right, now we need to put some probabilities onto those. So with the first one, we have 8 winning things available out of 12, 4 losing ones out of 12. Now let's follow that top branch along. We would have 7 winning ones left out of 11. Then we would have 6 left out of 10. This would be 4 out of 10. And so then our next branch along at the top here, we would still have 6 wins out of 9 available. And this one would be 3 out of 9. Now back to this point here, back on this branch, the opposite of 7 out of 11 would be 4 out of 11 of the losses left. Moving along to this win here, we've used up a win there, so we've got 7 out of 10 on this one and 3 out of 10 for a loss. For the win here, we would have 6 out of 9 left for the wins, 3 out of 9 for the losses. Okay, this branch here we're coming to now, we have, if we've picked a loss, we will have 8 out of 11 wins available, and a loss would be 3 out of 11. Next branch along this one, the win, we've used up a win, so that'll be 7 out of 10. This will be 3 out of 10. And the final pair over at the end, we've got 6 possible wins left in there out of 9, so this will be 3 out of 9. Now the owner wants it to be easy to win, so let's work out the probability of a win. So we want any route through this diagram that gives us 3 W's. So we've got this one here. We've also got this one just here. And I missed one in between. We've got this that goes win, win. Oh, I'm gonna stick to just the one color. That seems to have confused things. Whoops. Hang on. Here we go. So win, win, win. Then we've got win, win, lose, win. Win, lose, win, win. And then lose, win, win, win. Okay, so we've got 4 possible ways to get 3 wins, and we're going to add them all together. So that looks like this. I'll just pause to pop that in the calculator. That comes to 0.5939. Now that's, let's go back to answering the question. Is it relatively easy to win? It's a 60% chance of winning. It's more than a 50-50 chance. That would be considered a pretty good sort of chance in terms of these scratchy types of things. So just write something to that effect. Okay, on with question 2. We've got information about what was this? American men, and some details about whether they were a smoker or not and whether they died from cancer or not. Okay, now given that a male was formerly a cigar smoker, then calculate the probability he died from cancer. And sorry, I did miss that mention. It was here that this was about cigar smoking in particular. Okay, so the probability that they died from cancer, given that they were a smoker, is the probability that they died from cancer and were a former smoker. I should put their former smoker, divided by the probability they were a former smoker. Okay, so died from cancer and a former smoker is 91 out of the possibility that they were a former smoker is 7848. So 91 divided by 7848, 0.0116. Next we want to look at if a current cigar smoking male is more likely to die from the cancer than a male who has never smoked a cigar. So let's work out the chance of each. So the probability of them dying from cancer, given that they are a current smoker, is going to be, let's look up, died from cancer for the current smokers is 141 out of the total of current smokers, which is 7866. The probability that they die from cancer, given that they have never smoked a cigar, so never smoked, so that's looking for the ones that died from cancer and never smoked, is 782 out of all of the ones that never smoked is 121,529. Okay, so this one, 141 divided by 7866 is 0.0179. Actually, we'll include the fourth decimal place, fourth significant figure. 782 divided by 121,529. That's not right. Oh yes, sorry, missed the E at the end. So that's 0.00643. 5. Now for relative risk, we start with the more risky thing, that they were a smoker. So that's the, I'm going to leave it in fraction form actually, the 141 over 7866. We divide it by the less risky thing, or what we consider to be the less risky thing, so that's the non-smoking one. And we'll see how many times bigger it is. So 141 over 7866 divided by 782 over 121,529. Now we can see just from having worked out the numbers that their chance of getting cancer when they were a current smoker is more. We're just seeing how many times more. So that equals 2.79. Now let's write that as a sentence. That looks like this. Okay, now part 3. From this study, if you have been a smoker but then stopped, how is this likely to impact on your risk of dying from cancer? So we want to make a comparison of those 3 situations. So the probability of dying from cancer, given that you've never smoked, now I'm sure we've got that up here. Yep, so just right here is this one here. Just make that clear, it's a 0.644. The probability of dying from cancer, given that you were a former smoker. I don't know if we've got that. Let's have a look. Did we work that out in part 1? Yes, we did. So that was this bit here. Probability of dying from cancer, given that you're a former smoker, is 0.0116. And the probability of dying from cancer, given that you're a current smoker, we had just worked out in this one up here. So that's 0.0179. And you can see those probabilities increase as we go up each of those categories. So we can say a former smoker, or former cigar smoker, and we'll do the division. 0.0116 divided by 0.00644 is approximately 1.8 times as likely. And this is less than current smokers. Part B, we've got the likelihood of insurance company claims involving chemotherapy and radiation. So we'll have chemotherapy and radiation for all of the claims. The number of claims that the company receives for chemotherapy or radiation accounts for 75%. So probability of chemo or radiation is 0.75. Then the number of claims that don't include chemotherapy is 35%. So probability that it doesn't include chemotherapy is 0.35. Which makes the probability that it does include chemotherapy 0.65. So this whole circle here will make 0.65. Then the two circles combined have to make 0.75. So then this piece here must be 0.1. Now the other bit of useful information is that these two things are independent. Now, if they're independent, it means the probability of C times the probability of R will equal the probability of C and R. C and R being the overlap piece just here. Let's try calling that overlap X to represent the amount in there. Now, the probability of C is 0.65. We've got that already. Probability of R is 0.1 plus X. And that will equal the probability of C and R, which is the X that's in the middle there. Let's save ourselves some effort and go to equation solver for this one. Let's just clear that out. Right, 0.65 times by 0.1 plus X is equal to X. And solve. So X equals 0.1857. The last piece of the puzzle is calculate the probability that the claim includes radiation treatment. So this is the probability of R, which is X plus 0.1. So that's 0.2857. Okay, we have a game being played where we have a dice being rolled first, and if we get a 6, it stops. So I'm going to put that actually on the bottom branch for this one. Now, the chance of rolling a 6 is 1/6, and not getting a 6 is going to be 5/6. Now, if we get a 6, the game ends and you've won. If you don't get a 6, then your opponent tosses a coin. Now, if he gets, if he tosses a head, then he wins the game. So I'm going to pop head down here. Half, half. Tails would lose. So if he gets a head, then he wins. If he gets a tails, we do the dice again. So this would go not 6, 6, 5/6, and 1/6. Getting a 6, you would win. Not getting a 6, he has a go of tossing the coin, and so on like that. So that would, well, not that one. This branch would carry on doing those patterns. So then thinking about the probability of getting a win from that for you doing the dice part of the game, you could either win from this first branch here of getting the 6, or the next place you could win would be this branch here. If you don't get a 6, then he gets a tail, and then you get a 6. Then you would, the chance of that one happening would be 5/6 times a half times 1/6. The next way to win would be carrying that through. Don't get a 6, he gets a tail again, and then you get a 6. So that would be 5/6 half, 5/6 half, and then 1/6, and it's going to carry on like that. Now we can spot a pattern in this where we start with a 6, and there's always portions of 5. Let's do a different color there. Hang on. 5/6 times a half, and then we have 5 6 times a half. We've got 2 of them. In the next one we'd have 3 of them, and then each time it gets times by a 6 again. So this will be 5 over 6 times a half times by a 6. The next one will be 5 over 6 times a half squared, and then times by a 6. Then we've got 5 times a 6 times a half cubed times by the 6, and so on. Now, I'm going to finish this one slightly differently to the answers that are given in the D&D resource book, because the resource book uses something called a geometric progression. However, you aren't actually expected to know that, and the formula for it isn't on the formula sheet for statistics. If you know about geometric progressions, then you by all means can go ahead and use it on this question. But if you don't, you can answer this numerically, and I would expect that on the external that would get you a result that's close enough, particularly because as we do more of these will get more and like smaller and smaller. So adding on smaller and smaller pieces is going to make very little difference to your result. So I'm going to type these into the calculator and keep adding on more until we get something that's coming to roughly the same amount at the first few decimal places. So you can see what I've put in so far is just up to the squared term. So I can show you what I mean. We've got to a 0.265 at this point. Now let's add on another one. So 1/6, I'll just take out that bracket there. We want it just over here. 5 6 times a half to the power of 3 this time. And you can see we're getting closer towards this coming together. We're sticking with the 2 at the front here. Let's add on another one. 1/6 times 5 6 by half to the power of 4 now. And actually, to save typing it in again, we'll just take that answer now, add on to the power of 5, go back and add on to the power of 6, and you can see we're getting numbers that are tending towards 0.285 at the moment. So let's just keep going with a few more. 7, oops, we'll do an 8. We've got 0.2856. That's getting pretty spot on. If we can get this to 4 decimal places, that would be really good, so that it keeps coming out to the same number. So we've got 0.2857, and if we keep going, it's adding on very small amounts now, but it's not going to push us past the 7. So this is going to come out to, this will be, oops, I'm just going to put approximately equal to 0.2857. That's a particularly tricky question. I think possibly harder than you get on the external, but still doable. Okay, let's take a look at question 3. So we have this situation where Hazel could be paid $50 a month, or have 6 notes in a bag, one that's $100, 5 that are $10, and draw 2 out. So worst case scenario, she'd get $20. Best case, she'd get $110. And then there are variations in between. And she's deciding to conduct a simulation to see what would happen. Now, the first question is just discussing how carrying out the simulation would help her to make that choice. So let's put a couple of points down. So a simulation would show her all the possible outcomes and how many times she could expect those different amounts to come out in the long run. So that means she'd be able to see the variation in the different outcomes and the risk associated with them. So that variation, if it's tending to be quite a lot of variation, whether she wants to take that risk for potentially higher payout, or if there's not much variation, but maybe the payouts aren't going to be as high, she could take a look at those things. from that, she would be able to work out her expected average earnings and decide whether she would be better off or not from taking the $50 a month. Okay, so we've got a graph of Hazel's results here. Based on Hazel's simulation, what should she do? And looking ahead now, I've just realized when I was talking about this one, she can only get $20 or 110. I didn't think through. There is nothing in between, but it doesn't really change what I've put up here. Okay, so the graph that we've got, $20 came out quite a lot. $110, almost half as much. So for that one, it's looking like 2/3 roughly of the time she would be only getting $20, so you'd probably want to go for the $50 a month. And we can go a further step to support that and work out the expected amount of earnings from this. So we can do the expected earnings would be $20 times by the frequency we've got here is 69 out of the total was, this is a 69 and this is a 31. So she must have done that 100 times. And then we add in 100 times the likelihood of getting that one was 31 over 100. Sorry, $110, not 100 there. So we'll do 20 times by 0.69 plus 110 times by 0.31. So expected earnings here is $57.90, and that's less than the fixed $50. So that was the result of the simulation. This part C wants us to work out the theoretical probability when she picks the two notes. So on the first note, she could get 10 or she could get $100. There's 5 $10 notes, so that's 5/6, and there's one $100 note. If she picks a $10 note, she could pick another 10 or she could pick another 100. And from that one, there's 4 $10 left out of 5 and one $100 note. If she picked 100 first, she could only get a $10 note. So that would just be a chance of 1. So the probability of getting $110 can only be done by doing a $10 and 100 and then 100 and a 10. So we'll add those two together. So the top branch is like this, and then we add on 6 for the, it's a 6 times 1, but that doesn't, times by 1 doesn't change anything. All right, so 5/6 times 1/5 plus 1/6 is equal to a third. So now comparing those two results, in the simulation, we had the probability of getting $110 was equal to 31 over 100, 0.31 from the results of that. In theory, the probability of 110 was equal to a third that we just worked out. So those are pretty close. And the simulation was run 100 times, and we'd expect if we ran it for many, many more, then it would get closer to a third. Okay, so Hazel has said that she doesn't really want to take that deal. She thinks it's not in her favor. So she doesn't want to take the risk of doing that unless he replaces one of the $10 with a $20 note. Now, if Alec agrees to this, how will this change the probabilities and the likely amount that Hazel earns per month? So now there's an option where she could pick a 10, a 20, or 100. If we are picking a 10, there will be 4 of those out of 6, 1 20 and 1 100. Oops. 1 out of 6 is 20 and 1 out of 6 is 100. If she picks a $10, she could pick another 10, a 20, or 100. If she picks the 20, there's only a 10 or 100 left. And if she picks the 100, there's a 20 or a 100 left. And let's pop those probabilities on. After the 10, we've got 3/5 left there. For the 20, I'm just going to change the color to make sure we can see that. We'll have 1 out of 5 there. For the 100, we'll have 1 out of 5. Then 4/5, 1/5, and 1/5. And realized my mistake there. It's not a 100 at the bottom. She could pick a 10 there. There'd be 4/5. Okay, so let's work out earnings. So from this top one, she'd get 20, then 30, 110, 30, 120, 120, and 110. All right, so the probability of getting $20 is 4/6 times by 3/5. Probability of getting $30. We're looking at that top one there. That's 4/6 times by 1/5, and then we'll add on this other line that can get us 30 as well. So 20 and then a 10. So that is 1/6 times 4/5. I'll keep that as a fraction at the moment, just to preserve all the accuracy. The probability of getting next up would be 110. So that third line down, we've got 4/6 times by 1/5. And then add on the other way to get 110 is this bottom line. So 1/6 times 4/5. And finally, the probability of getting the highest possible amount of 120, we have these two lines next to each other just here. So we've got 1/6 times 1/5, and that's the same on the next line, so times that by 2. Okay, so now we can work out her expected earnings. We'll do 20 times 0.4 plus 30 times 4/15, 110 times 4/15, and 120 times 1/15. Comes out to expected earnings of $53.33. So this increases the amount she could expect to earn on average, and it's more than the $50, so it's better than taking $50 per month. That is the end of this practice external assessment from the D&D Resources. If you found this helpful, please like and interact and comment with the video, because it helps other people to find it too. They'll probably find it useful as well. And you can go to my homepage to find other resources to help you prepare for this exam. See you next time.